Okay, so this is a continuation from the first podcast that I created. So this would be part two. And the last time we talked, um, I mentioned how the size of an atom can dramatically change if you lose electrons or even gain electrons. Um, but here in this example, we encounter something unusual. So it says rank the ions K plus, Ca2 plus, Cl minus, and S2 minus in order of increasing size. And it's really hard. If you look at the periodic table and try this, you can't figure it out because this guy shrinks. This guy also shrinks, but by a magnitude of almost double because you're losing 2 electrons here. And here it's increasing, and here it's increasing by even more because it's gaining 2 electrons. So we can't really estimate the size and rank them, but they all have something in common. And this thing they have in common is that they all have the same number of electrons. So if you look at the periodic table, look, figure it out. K has lost 1, Ca has lost 2, Cl gained 1, and S2 minus gained 2, and they all end up with the same number of electrons. So when that happens, we call them isoelectronic. So iso means equal, electronic means same number of electrons. And when we undergo this unique situation, what we look at is the number of protons, so the atomic number, because that's never going to change. So when you do this, you look at the protons. So let's look at the periodic table. So periodic table. Periodic table. Ta-da. There it is. Right there. So K has 19 protons. Lithium has 3, sodium. So we're looking at K here. 19 protons. So K has 19 protons. Calcium has 20. Chlorine has 17. And sulfur has 16. Right, and they all have 18 electrons. So they all have 18 electrons, but what they have difference is the number of protons. So the more protons, the smaller the size. So when you rank these, the one that has the more protons would be the smallest. So which one is smallest? It would be calcium with a +2 charge. Then it would be potassium. Then it would be chlorine. And then it would be sulfur. So that's how you determine the size of these ions when they all have the same number of electrons, and we cannot use the trends that we normally use. Also know what isoelectronic means. Okay, it means they have the same number of electrons. So here in this slide we have agree or disagree scenarios. And what I want you guys to do is I want you to pause this and I want you to basically tell me if all 8 are true or false, and try to justify why. Okay, go ahead and pause. Okay, now that you did that, the first one says Coulomb's law says that as you pull charges away from one another, the attractive force increases. It's not that they're pulled away, it's they're attracted to each other. So that would be false. Coulomb's law says that the larger the charges, the more attraction there is, okay, among those charges, the larger the attractive force. So it's not that they're being pulled away, it's that they're actually being pulled towards each other. Okay, they're being pulled towards each other, and that's what causes the attractive force to increase. Number 2, the effective nuclear charge describes the attraction between the nucleus and the electron of interest, and that is true. It's another word for attraction between the nucleus and the valence electrons. Okay, it doesn't necessarily have to be a valence electron, even though most of the time we will be looking at that, but it could also be a core electron. 3, the effective nuclear charge decreases down a group, and we learned that as you move down, there's an increase in shielding, and that would cause the attraction to decrease. So that is a true statement. 4 is also true. Effective nuclear charge increases across a period. When we say across, we read it as left to right, and that's because you're adding more protons and the nucleus gets more positive. 5, the atomic radius is always larger than the atomic radius of a given atom. So the keyword here is ionic. So if something's ionic, it could be positive, it could be negative. It doesn't mean that it's always going to be larger. It could be smaller if it happens to be losing an electron. So if it loses an electron, it's going to be smaller. If it's gaining an electron, it's going to be bigger. So it's not always going to be larger. For 6, you were supposed to put true, because if we compare selenium and tellurium, we know tellurium is bigger based on the trend. Okay, so that means selenium on its own in its neutral form should be the smallest, and then because both of the ions are gaining 2 electrons, we have to use the trend here, and tellurium happens to be larger, so that's why we end up putting the tellurium with a negative 2 charge at the end. Negative means it's gaining electrons, going to be really, really big. Okay. The same situation for 7. 7 is actually false. Let's see why. So if we look at the periodic table, first of all of these 3 are positive, meaning they shrink. But if we look at the periodic table, cobalt and iron, cobalt should be bigger. No, cobalt should be smaller than iron. So iron is bigger. And iron is bigger, then that means cobalt should be the smallest. Come on, cobalt should be the smallest. And then iron is bigger because it's more to the left. As you move to the left, things get bigger. And then from there, we look at the charge, and we know that this guy with a positive 3 is going to lose even more electrons. So it's going to be the smallest of the 3. So the F is 2, and then, it's 3. Plus 2. So this is the trend. Fe plus 3, cobalt is the smallest, then Fe with a positive 2 shrinks a little bit, shrinks the most, and then Fe with a positive 2 doesn't shrink as much as this guy, because this guy loses 3 electrons, so that makes it smaller than this guy. So this should be the trend. And then for 8, 8 is actually true. So electron shielding can weaken the attraction between the nucleus and the valence electrons, and so can electron repulsion, because as the electrons are repelling one another, it generates a disturbance in the attraction. But we learned that the effective nuclear charge already takes that into consideration. Here's a quick write for you. So I want you guys to look at this and answer these 2 questions. Go ahead and answer them on the side, and then I'm going to explain what you should have gotten out of this. Okay, so as we look at the reds, we notice that Zeph is continuously increasing as we move from the alkali metals all the way to the noble gases, and then back again to the alkali metal, sodium, and still there's a linear trend. But when we look at it from the perspective of the green, which we're not looking at the 1s orbital, as it reaches a noble gas, Zeph goes down. Okay, why is that the case? And there could be multiple answers, but the point of this is to give a probable explanation. And my explanation is that when we're looking at it from the 1s orbital, we are not considering electron shielding. I'm sorry, we're not considering electron shielding. Or the amount of energy levels as compared to what's in green, because look, lithium, beryllium, boron, carbon, and then we hit the noble gas, neon. And then from here, you start to enter another energy level. And because of that, we're entering another orbit, another orbital, and that means that we're going to start to see the shielding effect take place. And so Zeph is going to decrease dramatically because of this electron shielding. And then as you're adding more and more protons, the attraction continues to grow, and then we're going to predict it's going to go down because you're moving into another orbital, into another energy level, and then we're going to see an increase again because of the effective nuclear charge increasing. So the point of this quick write is for you guys to think a little bit, for you guys to use the vocab a little bit. Again, we're trying to understand what is going on in the atom using data and graphs. This slide basically is showing us what ionization energy is. Ionization energy is the energy needed to ionize an atom. So the energy needed to remove an electron. So once you remove an electron, you become a charge, right? But we also see a trend here on the periodic table, and I asked you to memorize this, whereas you move to the right and up, the ionization energy tends to increase. Okay. So this is the trend. As you move to the right and up, there's more ionization energy. Okay. And I want us to go back to this idea of Coulomb's law. The question here is why? Why is it that as you move up, you need more energy to remove an electron? Well, it always goes back to Coulomb's law. As we move up the periodic table, we learn that the size shrinks. Okay, everything gets smaller as we move up. And if something is very small, very tight, then you're going to need a lot of energy to remove an electron because the nucleus is really holding on to those electrons. So the more smaller something is, the more energy you're going to need to pull an electron. We also learned that the more positive something is, or the more charge there is, the more attraction there is. So for example, here there's a +1, -1, and there's an attraction. Here there's a +2 and a -2, and there's an even more larger attraction. And then if we have a plus, let's say we have more positive charge here and more negative charge, then we're going to see an even greater attraction. So the smaller the atom gets, the more attraction, and the more attraction there is, the more energy you're going to need to remove an electron. So I'll repeat that one more time because that's basically the most important part. The more attraction there is between the nucleus and the outer electrons, the smaller the atom gets. The smaller the atom gets because of this attraction means that there's going to be more energy that will be needed in order to remove an electron. And that's why we see this trend. As you move to the right and up, everything gets smaller because there's more attraction. And because there's more attraction, you're going to need more energy to remove an outer electron. Here, based on the trend that you memorized, go ahead and answer this question. It should be very straightforward. Go ahead and press pause. Okay, now that you press pause, your answer should be this right here. Cesium would be the smallest, then potassium, and then lithium. Is that, oh, that actually does not sound right. Lithium would be the smallest, then potassium, and then cesium. Okay, so that's based on size. Okay, based on size, not ionization energy. Here's another example. Rank these from largest to smallest. Okay, hold on. Okay, so carbon should be the smallest. No, the largest. Carbon should be the largest. Then oxygen, and then fluorine should be the smallest because it's found all the way to the right. Yeah. So make sure you memorize that trend that I asked you to memorize at the very beginning of lesson 2.1. Okay? Alright, now going back, I want to go back to electron configurations. Here I want you guys to pause and write the electron configuration for lithium. So lithium on the periodic table would end in 2s1. So it will be 1s2, 2s1. So it should look something like this. And then the next question says, let's say you ionize this lithium, how would the electron configuration look like? And we learned that lithium is going to lose one electron. So it's going to lose this guy right here. So you could either completely get rid of this. So let me copy and paste it right here. You could either completely eliminate this, or you could put a 0 right there. Okay, they both mean the same thing. A 2s orbital does exist, it's just unoccupied, there's nothing there. So I just wanted to make that point, that you guys are allowed to subtract and add electrons. But then we come into a very unusual situation here. So we have to come back to this. It says here, write the condensed electron configuration for iron. So go ahead and pause and try it. Okay, so iron, the condensed one, iron is going to be right here. The condensed means we're going to move back until we hit a noble gas, and it's argon. So we're going to type in argon. And then argon is 4s2. Oh, 4s2. And then 3d1, 2, 3, 4, 5, 6. 3d6. Yeah, remember it moves down one energy level, so 3d6. Here it says, how would the condensed electron configuration look like for Fe plus 2? And you're probably saying, okay, plus 2 means we're going to remove 2 electrons, and we're probably going to remove them from here, so it's going to be 3d4. But here's a twist. Here is the twist, okay? It's actually not going to look like this. This is wrong. That is wrong. What you do is you remove the electron from the highest energy level first. So here we have energy level 4. Here we have energy level 3. Which energy level is bigger? It's the one with the bigger number, 4. So we have to remove electrons from that energy level first, and then we could get into the 3D shell. Okay, so this is the correct answer. Or another way to write it would be to just eliminate the 4s shell. So any of these two are correct. This would be wrong. Okay, and it tells you at the very bottom of your notes, new rule. When removing electrons, they are always removed from the occupied orbital having the largest principal quantum number, which is this number. Okay, so make sure you understand this because it's going to be on your test. We're going to do a little bit more practice with that. And then the next thing is the bond length. The bond length is the length between the nucleus of two atoms. So here's the nucleus of one atom, here's the nucleus of another. The distance would be the distance between those two radii there. Okay. For example, the bonding atomic radii are shown as follows for carbon and bromine. So the radii, the distance between the nucleus and the outer electron, is this, and for this bromine right here it will be that. So what is the distance? We just add up the two radii. So when we add them up, you get this. Okay. I know it sounds very simple, but you'll have some homework problems related to that. And I also want you to know that the larger the attraction, the larger Zeph is, the smaller the radius tends to be. Okay, so it says here, based on what you know about Zeph, predict the trend for bonding atomic radius. So let's see. So the bond radius should get larger as you move to the left because things get bigger, and down. So if they ever mention ranking something based on bond length, just think of it as the same as atomic radius. Okay, think of it as the same thing as size, because the larger the atom is, the larger the radius is, the larger the distance between the nucleus and the outer electrons. And based on that, you guys could start problem set 2.1. Make sure you get those problems done.